everyone, and welcome to today's Open Teams community event. Open Teams is the single point of contact and procurement for all your open source solutions, support, and training needs. Visit openteams.com or reach out to us at connect@openteams.com to learn more. As part of Open Teams' overall mission to sustain and support open source, we're also sponsoring the Open Source Architect community with the goal of providing a dedicated space for experts to connect and collaborate over their favorite open source tech. To learn more or to apply for membership, visit openteams.com/OSA-community. In today's event, Saul Shanabrook is going to present on equality, saturation, and equivalence graphs, or eGraphs. One of the key applications of the technique of equality saturation and the data structure of an equivalence graph is in identifying alternative but functionally equivalent expressions of a given computer program that provide improved performance of one kind or another, faster execution, better memory efficiency, and so on. Recent trends in data science and machine learning computation have been away from CPO workloads on local machines and toward executing code via a variety of specialized compilation and computation backends. In the PyData ecosystem, that's PyTorch, Dask, Numba, Ibis, and so on. The potential offered by equality saturation and eGraphs as a means to translate code initially written for small-scale on-CPU work to these contexts is significant. In this talk, Saul will go over how eGraphs work, how they were developed, and different ways they can be used in the PyData ecosystem. Saul will also survey the egglog library, which is one specific tool for using eGraphs in Python and other languages. Please post any questions you may have during the talk to the Zoom Q&A panel. And if anyone not already online is interested in participating in live Q&A with Saul at the end of the talk, let me know and we'll get you set up. Saul, go ahead and come back online. Welcome, and thank you for being here today.
Thank you, Brian. Thank you for the intro and setting this up. And I think I may have invited everyone with my link, so there's a bunch of Sauls in the chat.
That is all right.
I mean, the real Saul.
You wanted live Q&A, and now we have it.
Yeah. So I guess since everyone's in the panelists, you're able to talk and everyone can hear you. So you're welcome to ask questions throughout, and I'll also take some at the end. So let me just start sharing my screen. So yeah, this talk, I hope by the end of this talk, the goal is, if you don't know what an eGraph is, that maybe you'll have a little bit of a sense, and maybe you'll get a sense of what we can do with them in Python. So thanks so much for joining. And like I said, yeah, feel free to interject with any questions, confusions, or clarifying points. So I'm going to start with just a PyData kind of overview and then go into some more of the eGraph stuff to motivate the work. So people have probably seen this graph before, since this is more of a Python crowd here. And we like to talk about like an ecosystem in PyData. And so what does that really mean? I guess there's some kind of like analogy to natural ecosystems. It's interdependent, it's resilient to changes. It's not like a top-down orderly process, but more it's emergent. And if one project fails, it's not going to take down the whole enterprise. It's distributed in that way. So I find it fun to work in this kind of ecosystem that has these properties. And so some of my questions as someone building tools is, how do we support the ecosystem? How do the tools we build not only provide people with value who are using them, but also help the ecosystem as a whole become stronger? And how do they allow maybe greater collaboration between projects? So that's like kind of some of the framing that I'm coming at this with, even though it's a bit hot, kind of lofty. That's the part that is exciting to me. And I see egglog and the eGraph stuff as a way of sort of pulling in some programming language pieces into this community and kind of giving us a stronger foundation to build off of. And so it's also a way to tie together different groups of people who might not normally interact and help them solve each other's problems. So especially in the Python community, as we're thinking about different kinds of computation these days, it's not all, single machine execute on your CPU and CPython. There's distributed compute, there's many different kinds of like compilers, if you want to call them that, in Python. And so how do we have a strong theoretical backing for these tools that we're building? And what can we learn from the research that's being done? And how could some of that work help us? So that's kind of a high level overview of where I see some of this work possibly going, but it's very, experimental at the moment. Any questions or thoughts there before I move on to like particulars around eGraphs? Cool. So I'm going to start with some math people definitions. Sorry, I'll get to the visuals in a second. But I like this definition from Talia Ringer, who's a computer scientist, and she teaches a course on proof automation. It's on her course materials online, and this is from that class on proof automation in eGraphs. So she says that they're a wonderful data structure for managing equality and equivalence information. They are used in constraint solvers and automated theorem provers to implement congruence closure, an efficient algorithm for equational reasoning, but they can also be used to implement rewrite systems. So this is kind of like a lot to unpack in a little bit of text here. There's a lot of different words, some of them quite mathematical. So the first one, I'm going to, like the high level is like, okay, they come from theorem proving, programming language, mathematic background, but they can be used for rewrite systems, which can be used for compilers. So that's kind of like the high level overview of how we see like where they've come from and where they're going. But to go in a little bit deeper into this like congruence closure, like what does that really mean? So this is like another funny definition from Wikipedia, but it's so a congruence relation. So a relation is right. It's a way of saying what objects in a certain set are, would you say that are related to one another, and it's compatible with, in the sense that algebraic operations done with equivalent elements will yield equivalent elements, which sounds kind of cyclical, but what it's saying is basically it's a way of describing space, so that if you do an operation on two elements and any operation you do on two elements, if that operation will always give you the same result, an equivalent result, then those two elements are equivalent. It's kind of like a way of defining equivalence recursively based on their behavior. So we'll see how we can implement this, or how eGraphs implement this, looking at the Python library. So now we can get into some pictures, which might be more helpful. Here we have, we'll talk about some structure, and we'll talk about 3 items in that structure, A, B, and C. And we'll talk about an operation that takes 2 items and makes a 3rd item. So we can talk about the operation A on A and B, and operation on A and C, and we can view this, a visual representation of this eGraph. So one thing to note here is we can see, I don't know if you guys can see my pointer, but we have this operation is the operation from A to B. This one is from A to C. And you can see that each little node is also in another node around it. And so that this node stores all of the equivalent values. So here we've just defined AB as the operation of A and B. So we can see that they're equivalent, right? They're in the same class. So we have many different classes here. Each of them are equivalent, but they're not equivalent to each other, right? A and B are not equivalent. So now we can say, yeah, like, is AB and AC, are these equivalent? Well, no, because they're in different classes here, right? They're in separate classes, so they're not equivalent. Well, what if we made B and C equivalent? If we made B and C equivalent, then A and B, these 2 variables should be equivalent. Because if we go back to our definition, equivalence is kind of defined recursively. Algebraic operations done with equivalent elements will yield equivalent elements. So like if B and C are equivalent, then the operations done with them will also be equivalent. So we can try this out by running, we can union, we'll say, let's make them equivalent. Let's make B and C equivalent. And now look at our E-graph. So now we see B and C are in the same equivalence class. And we see AC and AB are also in the same equivalence class because they're both pointing to those. And we can check. So you can go back and forth and kind of see.
And so Saul, in this, it's not that you're taking the same system and kind of transforming B and C to become equivalent. You're considering a separate system where B and C are equivalent in the second case versus the first case?
So we're transforming it at runtime. We basically have a live data model that we're mutating. So if we reran this cell, they would look, or if it's the same underlying data system and we're mutating it and we're making them equivalent, if that makes sense. So they're no longer in separate equivalence classes. They're in the same one.
That doesn't invalidate its connection to whatever underlying system you're modeling or you're working with.
So that's the key, is you have to define equivalence in a way that makes sense semantically for your system. Mm-hmm. So whatever you're modeling, if you're defining things as equivalent, then that means calling some operation on one should result in the same value as calling that same operation on the other. Okay. So this case, we don't really have much semantics. So it's hard to say, like, what is B, C, and A? They're all kind of, okay. It doesn't, but that's
so this transform might work in some cases and not work in others.
You'd have to make it work. Whatever your domain is, you will define your equivalence in a way that makes it work.
Gotcha.
So you make up your own domain and you make up your own equivalence relations on it. And this framework doesn't give you any built-in ones. It just lets you define them how you like.
Yeah, okay.
That's a good point. It'll get a bit more concrete soon too. So yeah, this is the basic. Any other questions on this kind of like basic, or not basic, but it's like the core, it's really the core idea here.
Yes, so also the operation node that you have inside the equivalence class. Mm-hmm. By saying that the operation is equivalent, I'm assuming that means like the expression of the operation with A and B, like it's the value of the operation applied to A and B that's in that equivalence class, not like the nature of the operation itself.
Yeah, so this graph here, you'll see that the operation is pointing to A, and it's a little subtle in this diagram, but it's actually pointing to this whole class here of B and C. It's not pointing to B directly.
Okay, yeah.
So anytime you're pointing at something, you're always going to be pointing at an equivalence class. You're never pointing at an individual node, because you're saying that everything in that class, no matter what I do to it, it's going to be the same. Like, it doesn't matter which element I pick. Semantically, we're saying that it's the same, which are either one I use.
Yeah, got it. Cool.
So this is like the first part of our definition that dealt with this, congruence closure thing. That's kind of showing this part. Now we're going to look at the rewrite. What does this mean, implementing a rewrite system? Okay, so this is just, what I was saying, different E classes. So we're gonna now, it's a little bit more code, but we're gonna say, like, let's say for our model here, let's say that this operation is commutative. So anything, L and R is the same as R and L. Let's say that those are let's say it's like addition or something, right? This operation. So we can switch. So we can write a rewrite. We can say matching on any left and right operation. We want to rewrite that to right and left. And we can verify, hey, that's true. A and B now should be B and A. And we can see this in our graph. You can see the order. So this one is this node, this class first, then this one. And this one's the inverse, this one, and then that one. But they're in the same class, so they're equal or equivalent. So the rewrite rules, you can define rewrite rules, you can match them. And one thing to note is they'll run here until it's saturated, which means that any additional match doesn't change the graph. So it basically keeps running rules, all your rules, until there are no ops, until the graph is like fully saturated. So one thing that's interesting here is that running rewrite rules is only additive. You're not removing information like a normal rewrite system. Like a normal rewrite system, when you rewrite something, you kind of like lose the old one and you gain the new one, right? You're replacing it. And this looks similar, like the rule looks similar, but it doesn't actually behave that way. We're just adding information. We're simply adding a new equivalent value to the old value. So this makes actually a pretty big difference when you're defining rules, because it doesn't matter about the ordering. I don't care if I do this rule first and then this rule, or vice versa, because I'm only adding information. So I don't have to worry about kind of like choosing the right ordering of rules to get my right result. So this is a big difference between kind of traditional rewrite systems. We're going to try adding one more rule and showing also how to then take something out of the graph. So let's say C is an identity operation, like adding 0 to something, right? So we'll say rewriting C with anything is the same as C. So now when we run this, we see we only have 2 E classes now, basically C and these functions, and then A as a separate E class. And so now you might want to say, like, you've run these rules, but now you want to know, like, what's the value of something, right? Like the whole point is like, we've made up this graph, but like, who really cares? Like, I can't do anything with the graph, right? You kind of want to know, like, what is the value of something? So here I can say for the operation CA, which is here, right? Operation C to A, extract out the lowest cost value. So in this case, cost is very like, it's just like simple. It's like each node has a cost of 1. So it's going to extract out B, which is equivalent. So like in a traditional rewrite system, you do these rewrites and you get a new thing at the end. This is not like that. You do these rewrites and you build up this bigger and bigger graph. And then at the end, you can do some kind of query of the graph and choose out like your favorite expression with like the lowest cost or the best performance, or however you want to model what you want. So it kind of defers that choice until the very end and lets you just build up this kind of semantic knowledge. So to review, they store sets of equivalent items and you can implement rewriting systems on top of them. Order of rewrites don't matter, and then you extract out your best individual. So that's like the overview of eGraphs. You can see how they're kind of a mathematical data structure, but you could also kind of see how they're useful in things like compilers, because really what compilers are doing is finding equivalent expressions and then choosing the best one is one way to think about what a compiler is doing. So this is kind of like a way of a framework of holding that. So any questions on eGraphs? I'm going to go into the libraries now and the ecosystem a little bit. And I think I'll have another example coming up, which will help. But so like to take a step back, those are eGraphs. What's the deal with them? There was this library called egg in Rust that came out of University of Washington. And it was a couple years ago. And so it's a tool it's like a framework for building eGraphs in Rust that there's some different papers on it and some people are using it. And then there's a newer system called egglog, which is like egg combined with data log. And so this is like taking this existing eGraph thing and then adding on this component of embedding it in data log, which is like a way of talking about relationships. And so this allows you to have basically more performance and more expressivity in how you're matching. So I'll go into that a bit. But so what I'm going to be showing today is the Python bindings for egglog, which is this newer library. So this is not stable work in any means. It's based on academic work that's changing and etc. So I'm going to go into like some more like concrete examples now of this is egglog, and you might notice it says like egglog is like it's says it's a language-based design. So instead of being like an API, egglog is like this Lisp-like thing where you can write, hey, I have some type called math and I have these operations on it and I'm going to define them. So this is how you would write egglog. It's written in Rust, but you'd write it in this kind of Lisp-like dialect. And you can see, yeah, this is like a more concrete example of, hey, we have some number, right? And so we build expressions up about this number and we're going to write rewrites around numbers. And we can do the same thing in Python. So this is the Python bindings. It basically translates to the same Lisp-like language under the hood and executes in Rust, but you're able to write it with these nice Python-like type hints, and you can use the dunder methods. So I find it like a quite pleasant experience for authoring, and also you get all the benefits of an existing language, like you get all the editor support, etc. I mean, Python is very well supported, so it's quite nice to write it like this. So this is like an example, yeah, of some abstract, right? You have some expression 1, expression 2. You might notice that these are like semantically, they should be equivalent, right? 2 times x plus 3 and 6 plus 2 times x. They should be equivalent, but right now they're not. It doesn't know that they're equivalent, right? They're in separate e-classes because we haven't written any rules about what are numbers, right? It just knows that they're a thing with these operations. It doesn't really know anything about them. So we'll see, okay, this is the egglog version. I think I'll just skip this and go to the Python. So we can now define like, okay, what is a number, right? Well, first of all, numbers are, we can swap the operations for addition. We can distribute multiplication. So we can write some kind of like identities here. And we can also, when we have a number of an actual int, which is this definition, we can actually add the inner ints, right? And same with multiplication, because so now when we run these rules that we've just defined and we check, we can say, okay, now expression 1, expression 2, they're equivalent. They're in the same e-class. And it's a bit, it's not the easiest to follow all the arrows in the diagram, but, it's saying that, the multiplication of this and that is equal to the addition of, etc. So that's like one more concrete example of how we can think about these equivalence classes. So here we're not extracting anything, we're just checking. We're just using it to kind of like verify. You could see how this could be useful in theorem provers or stuff to like verify that certain properties are equal. Any questions on this piece here, a more concrete system? Is this making any sense, or is it confused? Does it make sense? Where are people at with this?
So just to make sure I'm understanding the visual language, when you have an operation that's that has 2 inputs, multiply or add, it doesn't matter for those 2 because they are commutative, but the order of arguments corresponds to the order left to right of the arrows, leaving that node.
Yeah, the order of the arguments corresponds to the order of the node. Those are just the separate args. So multiply, for example, this is its first arg and second arg. In this case, it doesn't matter which one's which, right? Multiplying it, but we haven't actually defined multiplication to be commutative. We've just defined addition to be commutative. We could, but we haven't yet. So
okay.
I don't know. Does that answer your question?
It does. I actually have a question from Travis Oliphant's on the line. He wants to know, are there any limitations to the objects you can include in the expressions? Like, could you do this with array expressions?
That's a great question. Yeah, I'm going to get to this a little later on. The built-in objects are ints, floats, strings, tuple, vectors, and maps. But I just added actual support to store built-in Python objects inside the egraph, so that we can store any kind of Python object we want and store it inside there. So it's preliminary, but yeah, that's what I was just adding.
So then you have to be more careful and precise about how you define the properties of those multidimensional objects, but it can be done.
Yes, and the other thing, the tricky thing is dealing with mutability. really, you want to treat the objects as immutable basically and functional, because if you mutate them, then old pointers to them won't be accurate, right? So that's another thing to kind of think about as we're adding other types of objects.
Mm-hmm. Are you aiming this at trying to be useful for optimizing tensor compilers and things like that?
Yeah, exactly. Like that would be a goal, is like, could we use this in any kind of the numeric? I have a scikit-learn example at the end that's not working, but is along the way. So I'll show that as kind of like could we build an object like this, feed it into something like scikit-learn, for example, and then use this to do some optimizations before actually executing the underlying code, is like one possible use case or way that this could be put in front of users. The other way is just like internal to libraries. So for example, Ibis is looking at using egraphs to like optimize their SQL. So there's kind of different ways this could be used, but.
Excellent. Yeah, that makes sense.
Okay, so I saw this before, but then I'll just show you again. We can also extract. So for example, here I'm extracting expression 1, and it gives us, this is just showing, gives us a nice, like a Pythonic representation. So if I executed this, I'd get back that value. So in the Lisp version, it just gives you this Lisp thing, and this gives you a nice Python expression. So this is, I'm gonna go, yeah, so this is the egglog, and then I'll go to the Python, but the multi-part rules, this is where I was talking about data log being useful, and this kind of like upgrade over egg. This is where we start to see it. So I'm gonna go to this, yeah, in Python here. So I'm gonna define a Fibonacci function, and so you can define the base cases, like Fibonacci of 0 is 1, Fibonacci of 1 is 1. And then we're gonna have a rule that it has to match on two different things, right? It says it has to match where we have Fibonacci of x and we have Fibonacci of x plus 1. Then we can define Fibonacci of x plus 2 as the sum of those. So this is where you can see it's kind of like SQL-y, right? We're like having a query. And so because it's built on this data log foundation, it can execute these queries in a fast manner and still run these rewrite rules. So this is one of the differences of egglog to egg, is it allows you to do these multi-part rules here. And I'll show some more examples of those later. Yeah, this we can define modules. So if we want to, I won't kind of get into this more in the weeds, but just, yeah, we can define some set of, functions and rewrites, and then distribute them on PyPy or something, right? And someone else could pull those in and then run some, and then construct some objects and run rules on them. So this is a way of, you asked a question before about like, is this mutating things? And so like, so far, all the examples I've had a live egraph runtime instance, and I've been editing it. And so this way of doing modules is like, instead of actually making an egraph, it's just saying, hey, these are some definitions. You can pull it into your egraph whenever you're ready to start executing things, to allow us to kind of distribute things and combine them more easily. So then, yeah, to Travis's question, this is the current API for storing objects. So if I have a Python object, let's say I want to store the value true in my egraph, like the Python value true. So I can call this save object. And this interface is quite low level at the moment, but we can see that what it does is actually stores the object. Basically in the Rust library, it just stores a reference to the Python object. And then in the egraph, how we point to it is by its hash of its type and its value. So then in the egraph, if you're pointing at this, you'll just be basically pointing at this function called PyObject with these two numbers, which represent a pointer to the Python object. And then we can go ahead and load an object from the egraph if we want. We can also, like, I've added some support for like eval, so we can evaluate arbitrary Python code using, calling not, for example. But this is a kind of a silly example, but the point is we can add more. This is just generic eval, but we could add specific methods to other Python objects. So something else I just added, which is very useful for the kind of like scikit-learn use case, is the ability to have certain methods on an E-class be like preserved, as in they're like real Python methods. They're not these like fake things that like, just build up expressions. These are like, they actually execute eagerly. And so this is useful if we wanted to find things that interface with Python. Like, for example, if you use an object and an if statement in Python, like if x, that'll under the hood call this bool operator, and it should give you a real Boolean, not like some expression that is a Boolean, but like an actual Python Boolean. So to kind of like write this, we can say, hey, for when you ask for the Boolean, we're gonna run the egraph with this expression and then extract out the equivalent Python object. So this is like, let's say we have two worlds here. We have the Python world and the egglog world, and we have to go between them. And so this is our way of kind of like of going back to Python when it asks us to. So we can say like, hey, okay, so if I try bool of true or false, okay, it gives me an error because so far we don't know how to translate between this egg true and Python true. Like we have no idea that those are the same. So we have to write some rewrites. So we can say, if I'm trying to turn true, the egg true into Python, then this should be the Python object true. If I'm trying to turn false, it should be Python false. And then I can also do some rewrites like true or anything is true, false or anything is false, is the value. So now if I call bool for true or false, it'll give me the proper Python value true. So this is a way we can write these egglog objects, but they can act like, it's kind of like lazy versus eager evaluation, right? When I need them, they can become eager and execute the graph. And also the nice thing is, like, let's say I had some other value x that's also a bool that someone else defined. I can see, hey, if true or x, well, this rewrite rule will trigger, so it'll be true. So I don't even know what x is in Python. It has no equivalent Python value. It doesn't matter because the rewrite rule executes and it becomes this true. So we can see this is, I just added a print to show that what the evaluation is here. So these are some building blocks. We'll see them kind of used in a second for some more, for the scikit-learn example. Any questions on this piece about saving Python objects? It's a bit funky at the moment, but. Okay, so the next piece is kind of the inverse of the previous one. This is like if Python needs something from your object. This is like if you're passing in a Python object, you don't want to always have to like upcast it, like, so for example here, what if I want to pass in like a false, like the Python object false to this OR operation? So I can say, hey, if I'm going from a Python bool to a bool in egglog, this is what the equivalent expression is. So this allows us, for things like, for example, like adding arrays, right? You might not pass like your particular array object as the second arg when you're adding arrays, but you want it to be, semantically, it is an array. And so you want it to be upcasted to an array. So this allows us to preserve the kind of like strong typing and semantics, but still allow different Python objects to be used. So now I'm just gonna, this was like a lot of kind of like detail. I'm gonna step back and just do another example, if that sounds good to people. But are there any questions first? I know there's a lot on the whole, there's a bit of a weirdness going between Python and egglog. It's a messy, kind of edge.
One question that I have, and I don't even know if it makes sense.
Mm-hmm.
If you have an object, a Python object that you've stored into the egraph,
mm-hmm.
would you do operations actually on the values of that object, or is it really only just you're concerned about the type? Like if you have an array 1, 2, 3, 4, do you are you modifying those values? Are you transforming those values at all? Or does that just not make sense because it's just all you need to know is that it's an array and maybe its size or something like that?
Yeah, that's a great question. I would say you could do it both ways. And in the example, I'm kind of playing with different ways of doing it. And it really depends on your use case. So you could go in there and build up expressions in the eGraph and then execute it kind of like eagerly, and actually execute every operation on the array and just do that, translate each of them back to like a NumPy operation. Or you could kind of just execute it symbolically and do something else and say, maybe feed it to Numba or something when you're done.
That was kind of where I was thinking towards, is whether you want it to actually carry out a computation for you, or in the application of transforming code for improved performance, seems like you want that generalized application.
Yeah, and this is where it's like, this is very much a low-level framework, and it could be used for different use cases. And so it's really about finding some of those initial use cases to start playing around with. Where could it actually be useful? Because it is quite flexible.
Okay, thank you.
So I'm going to go through another little example here just to kind of like tie together some of these concepts. This is a different way of representing Fibonacci. And we'll see we have similar rules. We're setting Fibonacci of 0 to 0, Fibonacci of 1 to 1. And we're saying if we have Fibonacci of x, then we can set Fibonacci of if we have Fibonacci of x, then we can set the Fibonacci of x to x minus 1 and x minus 2 plus x minus 2. So it kind of like builds it backwards. So we'll see we have the start here. We have Fibonacci of 1 is equivalent to 1. Fibonacci of 0 is equivalent to 0. So hopefully these graphs are starting to make sense. Kind of able to follow what they mean. So definitely pause me if it's confusing. So then let's say we want to get Fibonacci of 4. So we add this to our eGraph, and right now we just have Fibonacci of 4, but we know it's this variable f4, but we don't know what it is. There's no number, right? We just know that this exists in the eGraph. So then we can do one run, apply all the rules once, and we can see, okay, our definition was applied. So Fibonacci of x, we can rewrite that as Fibonacci of x minus 1 plus Fibonacci of x minus 2. And we can see that this is now in our eGraph. All right, so these are equivalent. It's a little odd because we're no longer saying like it returns a value. We're just saying it's equivalent to a value, basically. So now you might, okay, so now basically I'm going to apply it again. It's going to apply it recursively to Fibonacci of 3, Fibonacci of 2. Those will each be evaluated. So now we see, yeah, Fibonacci of 3 is, Fibonacci of 2 plus Fibonacci of 1, blah, blah, blah. And now we're seeing also, now we have Fibonacci of 2 is the addition of these two. And these actually have numbers in them, right? 0 and 1. So when we evaluate it again, we'll see that Fibonacci of 2 will have an actual number in it, right? And that will be 1. So we can see the Fibonacci of 2 here is now evaluated to 1. And that's actually the same as the Fibonacci of 1, right? They're both equal to 1. So they're in the same E-class. So now we're building up and we can see, okay, we're adding this to itself for Fibonacci of 3. And we get 2. And then finally, we can evaluate the last one and it gives us 3, and we can extract it and we can see we get 3. So now that we've done like a few kind of like small examples, I was going to show like, let's see how much time we have, 1:40. I'm going to go through most of this. I'm going to leave some time for questions, but Basically, I'll go through a little bit of a vague story. It's more of like a narrative. It's not, it just gives you an idea of how this could be used. And I realized when I was proofreading it that I got something terribly wrong in the definition, so I'll also point that out. But let's say that someone writes an ND-array module and they implement ND-array and they have, wonderful methods like get item and shape on it. And they implement an arange function. So we can define the how arange operates by defining the shape and indexing on arange. So, the shape of arange 10, for example, is just the vector of 10, right? And indexing into arange is just the index itself. So this is kind of fun. I mean, as a definition, it lets us a while back, we were working with Lenore Mullen, who built this mathematics of arrays, which is basically from 1988. Her thesis was on formalizing the mathematics of APL and how we can think about what's the semantic structure of arrays. And this is how she defines arrays, basically, as these two functions of get item and shape. And so we can kind of translate that, you can see quite naturally here, where we can define array operations just using these functions based on their behavior. So you can use this module, right, by adding it to your egraph, defining a range of 10, and then getting its shape, for example. You can see its shape is the vector 10. So not that useful, but let's say someone else goes along and implements a cross-product library. It's in a separate PyPy module. And this is where I realized I got the definition of the cross-product wrong, so don't mind this. I gave up. I had this in a previous talk and I didn't notice until now, so shows you that no one really looks at slides in a talk, I guess. But basically, you have a cross-product. I can define a similar kind of mathematical definition. And I can execute it, and okay, I see maybe it's wrong, but it does something. So I go ahead, and I'm a third person. I depend on these libraries, right? And I write my special data science application. It's kind of like a scikit-learn operation, right? And I call cross product on two values, and then I index it. And I can see I can execute it, with my functions, and it gives me a value. But I find, oh, this is too slow, right? It's like running all these rewrites every time I run it. It's kind of silly. I wanted to maybe symbolically evaluate, right? So let's say that someone else writes a library for delayed execution just based on the ND-array. They don't know about the cross product. They're just using this ND-array library. And, basically they represent everything as a string of computation instead of an actual value. So now if I use their module, I can pass in some string X, and I can see I can get a result back that's like a symbolic version, right? And so I could further specialize with this with the cross product. Even though the cross product and the symbolic were written in different libraries, I could write rewrites that use both of them. So this is the story's kind of silly, but the moral of the story is the goal would be to allow people in different libraries to independently write APIs and also rewrites of those APIs and build on one another in a way that's composable. Right now, I can't really write rewrites along Dask expression graphs. Right? I don't have the power to do that as a user, right? I don't really have the power to do that as a third-party library. The same with Ibis or any of these other libraries. They're all kind of internal details, which makes sense. But if they could share some more of their framework, then it could allow different people to pick up pieces from parts of them and rewrite between them or execute optimizations. So that's kind of the high level an idea.
Yeah, so this is a very coarse analogy, but what comes to mind is LaTeX typesetting, where the syntax you use to construct an expression has semantic meaning to it, even though multiple different things, multiple different input syntax can give the same rendered output. For something like Dask, where you have kind of the outer surface of the API where you don't necessarily know what was underneath it. If those internal details were exposed, then this kind of approach would let you reach under the hood in a structured and consistent way and do more with what's there.
Yeah, exactly. It's a way of like talking about the external API and the internal API in one kind of conversation to allow you to move between them more easily. Yeah. And so I wanted to show like I just started this yesterday, so it's nothing's working, but there's some interesting examples here. So this is the scikit-learn example for using the array API to do LDA. So this is just with NumPy, right? I pass in a NumPy array and I get some result back. And I can do their examples and their docs, or you can pass in a CPy array, you can pass in a PyTorch array. And scikit-learn will work with it because it uses the standard array API. So the question is, could we write an array API like this in egglog and feed it into, like, say, this fit function? Could we do that like in a mostly symbolic manner, right? So it's not actually doing much of the work by the end. It's just giving us a representation of what the result would be. And so there's some kind of like it was very fun to start working on this. When sklearn runs this function on your types, it does a lot of like kind of like checking, right? It wants to make sure the shapes are right and the size is right and all these things, right? So even if I have this symbolic thing, like it won't be able to execute unless it knows some things about the arrays, even if it doesn't know their whole contents, right? It needs to know, like, you know, blah, 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 dimensionality, all this stuff. So what I fed it was like, all right, let's give it some particulars just about, like, you know, some metadata, basically. Like, let's feed it the D types of each array. Let's say, okay, they're both finite, the sum of them. The unique values of the shape is, the shape of the unique values is 3, just like a bunch of random stuff that popped up that it needed to know. So this is basically when we saw before that bool thing. It's like, it's trying to get at stuff. It's saying like, if the shape of this is equal to that, and it's like, I need to know that value now. I can't be lazy, right? So this is what I'm kind of doing, is filling in these values so it can get to the point where it can execute. And so it lets, like, so I have to define all these functions like reshape, etc., right? And I can see, like, it's kind of fun. You get to define these identities basically for these functions. So, like, for example, we can say, like, reshaping, the D type of reshaping something is the same D type as the input. Or the length of the shape of reshaping is the same as the length of the shape that you passed into reshape. Right, and some special cases, like this is an example where we're using the multi-pattern matching. So I say, if I'm reshaping something, right, to the tuple of -1, which is just saying, all, you know, one dimension with everything in it, then the shape of that is going to be just, and the shape of the thing I'm reshaping is just one dimension, then it's the same. It's not doing anything. Right? If I already have something that's one dimension, I'm just saying reshaping everything so it's in one dimension, that's the identity, right? So this is kind of nice. You can write these rules that there's no, like, there's no difference in metadata and data. It's all just expressions, right? And we can evaluate the ones we want to eagerly, and we can maybe not give it the ones we don't want to. We can have those be lazy. So we can just have it basically get the metadata it needs to run these rewrite rules. So I'll show like a few, these are like examples that they're really a bit long, but, you know, these are things that actually, you know, like the sklearn is checking, right? So there's all these as arrays mixed in, but it's saying like reshaping Y into this, you know, single dimension, the number of dimensions sorry. Is it saying the number of dimensions is 2? Yeah, it's false. Okay. Yeah, that makes sense. So you can see it's kind of like checking all this metadata. So this is basically where I'm at with the sklearn example, is trying to get it through all this metadata so that it can actually give us the result, or a symbolic version of the result. So that's kind of an interesting example because it's very practical. It's very in the weeds. It's there's a lot of funky stuff that NumPy and scikit-learn do to mess with your array that you pass in. But this is just kind of like one example of like, if I want to expose this to end users, could they use this today using the array API without having to do any changes to underlying libraries? That's like one path, a separate path would be having those underlying libraries use this tool to do their own rewriting. So that's basically where I'm at. Thanks for attending, and I hope you learned something about egraphs and it wasn't too boring. And you're welcome to install the library and try it out, and happy to chat more about ways that this might be useful. I see some questions too. And
yeah,
we can, I guess, promote, I think Travis is the only one as an attendee, so we could promote him to a panelist.
I suggested he's driving, so
okay.
Yeah, that's not going to work. But he
Yeah,
he has another question. I actually have a question of my own. Does anybody else have some questions for Saul before I jump in with those two?
I have a quick one, if you don't mind. So just Saul, if you did have this like array API implementation that you're working on, like that's pretty universal, right? If you get these rules correct, like they're not specific to scikit-learn's LDA implementation. So I'd imagine like all of these rules, like a huge database isn't going into some library somewhere that people could use. Is that kind of is that a direction that would make sense?
Yeah, exactly. Yeah, and the nice thing is that these rules could be shared across array implementations because they're just symbolic. Like you could imagine executing these rules and then going to PyTorch and then going to NumPy. But because it's at the symbolic level, we don't have to, we can be more generic.
Yeah, that was one of the questions that Travis raised, is would it make sense to use this or promote it as part of the data APIs development efforts? Seems like.
Yeah, I mean, we'll see if it works. That's why I'm trying to get this, seeing if I can get an example working. I think it really meshes well with the existing array API like work that's been done in NumPy, from like the array dispatching to now the data APIs. Like you can see how it plugs in very nicely, and they can kind of like be nice companions to one another in a way, because this is really talking about more the semantics. So the array API is just like, the shell. This is your shell, and this is more saying like, okay, we have a shell, but like, what does the shell really mean? Like, what do all these operations really mean? Semantically, is there a way we can define them? Because like ideally, it would be nice if you could write an array, like not that this is maybe even useful technically, but if you could write an object that does get item and shape, like you should be able to build all of NumPy on that object, right? Whatever that underlying object is. All the rest of it, I guess the idea is all kind of just like semantic building on top of that. Or is one way, that's kind of like an overgeneralization maybe, but yeah.
So another question in the chat from TF, how hard is it designing APIs from Rust that are exposed in Python, and what considerations do you have to take into account when you're building Python that way?
Do you mean designing APIs from Rust? Do you mean like how hard was it to write the bindings from the Rust APIs? It was my first time. I was learning Rust as I was doing it, so it's a bit of a learning curve. But I actually liked Py-O3 quite a lot, and it seems a lot nicer than writing C extensions, at least. So it's kind of fun. What considerations? Yeah. Does that answer your question?
Right. So another question that Travis asked, going back to where you're at, with your initial effort with sklearn, how much effort would it take from here to get to a place where you could optimize a code block that is a combination of Dask and Numba together?
Oh God. That's a good question. I think it would be helpful to see some particular use case of that. That seems like a fun, that could be like a compelling user story around it. I think it would depend on the particulars, I guess. It's hard to know in the abstract. Yeah, there's some other work I was doing with this to try to, you could also kind of build something like Numba with this, but that's even more work because then you have to basically translate Python semantic. You have to like, you're kind of end up, but what Numba is doing, right, is basically representing the semantics of CPython interpreter, which is a huge task. So, yeah.
I mean, from what I was reading before your presentation, it seems like that the eGraph approach, the equality saturation approach, would be an alternative to Numba.
It could be like you could build something like Numba with this, for example. Like Numba could use this internally. They have their own IRs that they're translating between, and they have their own optimizations and rewrites. So that's like, they could do that. You could build something like Numba with this. You could also use this to build up a Python string and then send that to Numba and have that compile.
Okay. One last question I had. So in the discussion of this semantic representation of objects in the eGraphs, it was evoking pretty strongly the idea of property-based testing, like the hypothesis package.
Yeah.
Is there an actual similarity there? How do the two ideas, eGraphs versus property-based testing, how do those relate?
Well, it's similar in that you have like these wildcards, basically, right? You have these things that could be anything, and then you're writing how they behave based on these like variables, right? Which is similar to property-based testing. I mean, the big difference, right, is that this is property-based testing is kind of like verifying some underlying computation, right? And this is the computation. It's defining it. So instead of verifying, you're just defining.
Yeah, that makes sense. That makes sense.
So at SciPy, one of the someone involved in the Array API project mentioned that they have a hypothesis test suite for the Array API. Just wondering if you could use that as like a point to translate, like if you translate the hypothesis tests that they're already using for the Array API into rewrite rules.
Yeah, because the tests, I guess, are saying like given these inputs, it should have this output.
That's what I presume they're using hypothesis for it.
Yeah, no, it's true. There is like I hadn't really thought about that.
Use eGraphs to do rewriting of the hypothesis test suite into an eGraph representation.
Yeah, exactly.
All right. Well, we're coming up on the hour. One last question from anybody, or are we about done? I don't see anything. So okay, we'll call it then. Saul, thank you so much. That's all for today's event. We're recording the event. The video will be live on OpenTeams' YouTube channel as soon as we can get that worked up. Subscribe there to be notified when that gets posted. And if you want, feel free to ask further questions in the comment thread there. We'll keep an eye on that. Please check out openteams.com to learn more about OpenTeams and our offerings, and we'll see you next time. Thank you, Saul, and thank you everyone for being here. Have a good one.
Thank you, everyone. Take care.